Welcome to this problem-solving session. Today, we'll dive into LeetCode problem number 554, titled Brick Wall. We'll break down the problem, explore various approaches, and understand the most efficient solution. Let's get started. In this problem, we are tasked with minimizing the number of bricks that a vertical line will cut through in a given brick wall. The wall is represented as a 2D list, where each row is a list of integers indicating the widths of the bricks in that row, laid out from left to right. The challenge is to determine the optimal position for a vertical line that will pass through the wall from top to bottom, such that it cuts through the fewest bricks. Importantly, a vertical line only cuts a brick if it passes through the brick itself, and not if it aligns perfectly with the edge between two adjacent bricks. Our goal is to calculate this minimum number of crossings. For example, consider the input wall composed of 6 rows, where each row specifies the widths of the bricks. Drawing the wall visually, you can see how the bricks are arranged. Now, if we place a vertical line at certain positions, such as after the first brick of width 1 or after the second brick of width 3 in the first row, the line might align with brick edges in other rows. This alignment ensures that fewer bricks are crossed by the line. In this specific example, the optimal position for the vertical line results in crossing only 2 bricks, which is the minimum possible number. On the other hand, if the wall is constructed such that each row contains only 1 brick, like in the second example, the vertical line has no choice but to cut through every single brick. Since there are 3 rows and each row contains just 1 brick, the line crosses all 3 bricks, which is the minimum possible in this scenario. This demonstrates how the arrangement of the bricks directly impacts the solution. The problem also comes with some constraints that guide its implementation. The wall can have up to 10,000 rows, and each row can contain up to 10,000 bricks. The total width of the bricks in a row is limited to 20,000. Each brick's width is guaranteed to be a positive integer. These constraints highlight the importance of designing an efficient solution that can handle large inputs. Additionally, edge cases such as a single row, a single column, or uniform brick arrangements must be considered. For example, in a single row wall, the line can be positioned at any brick edge to avoid crossings, whereas in a single column wall, it must cross every brick. Uniformity among rows allows us to take advantage of aligned edges to minimize crossings. Efficient handling of these scenarios is critical for solving the problem within the given constraints. Let's start by breaking down the 2 approaches we can use to tackle this problem. First, there's the brute force approach, which is based on the intuition that we could try placing a vertical line at every possible column position along the width of the wall. For each position, we would check every row to see if the line intersects a brick. This involves simulating the entire wall and essentially performing redundant checks at positions where no valid brick edges exist. While the space complexity here is minimal, requiring no additional data structures, the time complexity is quite high, at n*m, where n is the number of rows and m is the average number of bricks per row. This inefficiency stems from the fact that we're examining positions that don't contribute to a solution. Now, the optimized approach takes a different perspective. Instead of focusing on all column positions, we shift our focus to the edges between bricks, as the goal is to find a vertical line that passes through the most gaps, minimizing the number of bricks it intersects. By using a hash map, we can efficiently count how many brick edges align at each position. With this data, we can determine the position with the maximum edge count, and from there, calculate the result as the total number of rows minus this maximum count. This streamlines the process by targeting only the relevant positions, cutting down on unnecessary operations. Analyzing the efficiency of the optimized approach, the time complexity remains n*m, as we still process each brick in the wall, but it avoids the redundant column checks inherent in the brute force method. The space complexity is p, where p represents the number of unique edge positions across all rows. This additional space for the hash map is small in comparison to the input size. The reason this approach is so efficient is that it zeroes in on the valid edge positions, skipping over irrelevant areas entirely. We chose this optimized strategy because it leverages the structure of the input data to focus only on the brick edges, ensuring significant performance improvements while maintaining clarity and correctness. By reframing the problem to count edge alignments, we unlock a direct and linear time solution relative to the number of bricks. While the trade-off is the additional memory used for the hash map, this is negligible compared to the computational savings achieved. The key insight here is realizing that we don't need to evaluate every possible vertical line position. Instead, we concentrate our efforts on the most common edge positions, minimizing unnecessary calculations and ensuring the solution is both efficient and elegant. In this problem, we're working with a brick wall represented row by row, where each row is essentially a list of brick widths. The challenge is to draw a vertical line from the top to the bottom of the wall such that it crosses the fewest number of bricks. To achieve this, we need to focus on the edges between bricks since a vertical line can only pass through these edges, not through the middle of a brick. The task boils down to finding the vertical position with the maximum number of edges, as this will minimize the number of bricks that are intersected. To prepare, we can pre-process the data by calculating all possible edge positions, which are derived from the prefix sums of brick widths in each row. Importantly, we skip the final prefix sum for each row because the edge at the very end of the wall doesn't contribute to our solution. This pre-processing sets the stage for solving the problem effectively. After determining the edge positions from the brick widths, the next step is to count how frequently each edge position appears across all rows. We use a hash map for this, where the keys represent edge positions, and the values represent their respective frequencies. For every edge we calculate, we simply increment its count in the hash map. Once we have the frequencies, we can identify the optimal position for the vertical line. This will correspond to the edge position with the highest frequency, as it represents the line passing through the most edges and thus intersecting the fewest bricks. If no edges exist, such as in the case of a single row with one brick, then the line will intersect all bricks. Finally, to determine the result, we subtract the maximum edge frequency from the total number of rows. This gives us the number of bricks the line intersects. By reducing the problem to counting edge frequencies, we simplify what initially seems like a complex geometric problem into an efficient counting problem. To implement this approach, we rely on two main data structures. The first is a hash map or dictionary, which efficiently stores and retrieves the frequency of edge positions. This allows us to quickly update and access edge counts during our computation. The second is a simple list, which we use to calculate the prefix sums for each row. These prefix sums help us determine the edge positions for each row. Let's walk through an example to see this in action. Consider the input wall 1, 2, 2, 1, 3, 1, 2, 1, 3, 2, 2, 4, 3, 1, 2, 1, 3, 1, 1. For the first row, the prefix sums are 1, 3, 5, which represent the edge positions before the last brick. For the second row, the prefix sums are 3, 4, and for the third row, they are 1, 4. As we process each row, we collect these edge positions into our hash map, building the frequency counts step by step. Continuing with the example, the edge positions for the remaining rows are as follows. For row 4, it's 2, for row 5, 3, 4, and for row 6, 1, 4, 5. Once we have all the edge positions, we use a hash map to count their frequencies. In this case, edge 1 appears 2 times, edge 2 appears once, edge 3 appears 3 times, edge 4 appears 4 times, and edge 5 appears twice. The edge with the highest frequency is edge 4, which occurs 4 times. To calculate the result, we subtract this maximum frequency from the total number of rows, which is 6. So, the number of bricks intersected by the optimal vertical line is 6 to 4, which equals 2. This means the line crosses only 2 bricks, which is the minimum possible for this input. The output for this example is 2. This step-by-step process demonstrates how the algorithm efficiently identifies the best vertical line position by focusing on edge frequencies. Analyzing the time complexity, calculating prefix sums for all rows takes O(n), where n is the total number of bricks in the wall. Counting edge frequencies using a hash map also takes O(n), as we insert each edge position once per brick. Therefore, the overall time complexity is O(n). For space complexity, the hash map requires O(k) space, where k is the number of unique edge positions. Now, let's consider a few edge cases. If the wall contains only a single row, the line will intersect all bricks except where the edges align. For walls with uniform brick widths, edges will align perfectly at regular intervals, simplifying the calculation. If the wall is empty, the result is 0 by default. Finally, we can optimize further by skipping computation for rows with only one brick or by terminating early if an edge position reaches the maximum possible frequency, which is equal to the total number of rows. These optimizations ensure the algorithm runs efficiently even for edge cases and large inputs. The provided Python implementation efficiently solves LeetCode problem number 554, brick wall. Let's break it down step by step. 1. Imports. The default dict from the collections module is imported. This is used for counting edge positions efficiently without needing to check if a key exists in the dictionary. 2. Class and function definition. The class solution and its method LeastBricks are defined. The method takes the wall, represented as a list of lists where each inner list contains the widths of bricks in a row. 3. Edge position calculation. A default dict named edge_counts is used to record the cumulative positions of edges, excluding the last brick in each row. For each row, the code iterates through the bricks, summing their widths to calculate the edge positions. These positions are stored in edge_counts with their frequencies. 4. Handle edge case. If no edges are recorded, meaning the wall has only one brick per row, the dictionary will remain empty. In this case, the vertical line must cross all rows, so the function directly returns the number of rows, len, wall. 5. Determine minimum bricks crossed. The maximum value in edge_counts represents the position where the most edges align. Subtracting this maximum from the total number of rows gives the minimum number of bricks crossed by the vertical line. 6. Return result. The function returns the calculated result, which is the fewest number of bricks crossed. This implementation is efficient, with a time complexity of O(n), where n is the total number of bricks in the wall. The use of edge counting ensures we avoid redundant calculations, making the solution both concise and optimal. Here, we start with the Java implementation of the solution to the brick wall problem. First, we import the necessary utility classes, such as java.util**. In the solution class, we define the LeastBricks method, which takes a list of lists of integers representing the brick wall as input. The goal is to minimize the number of bricks that a vertical line crosses. To achieve this, we use a hash map called edgeCounts to keep track of the frequency of edge positions where bricks end, excluding the edges at the far right of each row. Next, we iterate through each row in the wall. For each row, we initialize an edge position variable to 0. This variable will help us calculate the cumulative position of brick edges as we move through the row. Inside the loop, we exclude the last brick of the row because we don't want to count the far right edge. For all other bricks, we increment edge position by the width of the current brick and update the edgeCounts map. If the edge position already exists in the map, we increment its count, otherwise, we initialize it with a count of 1. This allows us to keep track of how many rows have an edge at a specific position. Lastly, we handle cases where there are no edges recorded. In such scenarios, we simply return the total number of rows, as any vertical line will cross all the bricks. Now, to determine the optimal vertical line placement, we calculate the maximum number of edges that align at any position using the values in the edgeCounts map. This is done using the collections.max method, which finds the highest frequency of edge positions. Once we have the maximum frequency, we subtract it from the total number of rows to get the minimum number of bricks that a vertical line would cross. This is because the most aligned edges represent the positions where the fewest bricks are crossed. Finally, we return this result. The implementation is efficient, leveraging a hash map for constant time updates and lookups, ensuring the solution handles larger inputs effectively. In this problem, we aim to draw a vertical line through a brick wall such that the line crosses the fewest number of bricks. The wall is represented as a list of rows, with each row being a list of integers that indicate the widths of the bricks. Importantly, the vertical line cannot run along the edges of the wall itself, meaning it must pass through the interior of at least one brick. To solve this, we calculate the positions of the edges of the bricks, excluding the rightmost edge of each row, and determine which edge position has the most alignment across rows. By subtracting the maximum number of aligned edges from the total number of rows, we can find the minimum number of bricks that the vertical line will cross. For example, consider this input wall. Each row of numbers represents the widths of bricks in that row. Our task is to process this data to find the optimal line placement. To solve this, we start by initializing a dictionary, edge_counts, to store how many times each edge position appears across all rows. Then, we process each row one by one, calculating cumulative edge positions while ignoring the last brick in each row. For instance, in the first row 1, 2, 2, 1, the cumulative edge positions are 1, 3, and 5, which we add to edge underscore counts. Continuing to the next row, 3, 1, 2, the cumulative positions are 3 and 4, so we update the dictionary accordingly. Repeating this for all rows, we end up with edge underscore counts showing the frequency of each edge position. The maximum frequency in edge underscore counts is 4, meaning the most aligned edges occur 4 times. To get the result, we subtract this maximum from the total number of rows, which gives 6 minus 4 is equal to 2. This means the vertical line crosses 2 bricks in this case. The process is straightforward, and the dictionary helps us efficiently track edge alignments. Now, let's consider an example where every row is fully aligned. Here, the wall consists of rows like 1, 1, 1, where each brick has the same width. As before, we initialize an empty edge underscore counts dictionary and calculate cumulative edge positions for each row, excluding the last brick. For the first row, the positions are 1 and 2, which we add to the dictionary. The same positions appear in the subsequent rows, so their counts in edge underscore counts increase to reflect this alignment. By the end, the maximum count of aligned edges is 3, equal to the total number of rows. Subtracting this from the total rows gives a result of 0. This makes sense because the vertical line can pass through perfectly aligned edges and avoid crossing any bricks. This example illustrates the optimal scenario where no bricks are crossed. Finally, let's look at a case where there are no aligned edges between rows. In this wall, the first row, 5, has no internal edges, so the dictionary remains empty after processing it. The second row, 3, 2, introduces an edge at position 3, which we record. The third row, 4, 1, adds an edge at position 4. At this point, edge underscore counts shows that each edge position occurs only once. The maximum number of aligned edges is therefore 1. Subtracting this from the total number of rows, 3, gives 3 minus 1 is equal to 2. This result indicates that the line will cross 2 bricks, as there is no edge alignment to reduce the number of crossings. This example highlights how the algorithm handles cases where alignment is minimal or non-existent. To analyze the time complexity of this solution, we start by considering the outer loop, which iterates through each row of the wall. If there are n rows in the wall, this loop contributes n iterations overall. Next, within each row, we have an inner loop that processes each brick, except the last one. Since the total number of bricks across all rows is m, the inner loop contributes m operations in total. For each brick processed, the edge position is updated, and the corresponding count in the hash map edge underscore counts is increment. These operations are constant time, 1, for each brick. Finally, after processing all rows and updating the hash map, we find the maximum value in edge underscore counts. This requires a single pass through the hash map, which has at most m entries, leading to an additional m operation. Combining these, we have 3 components, n, for the outer loop, m, for the inner loop, and m, for finding the maximum in the hash map. When we combine these components, the overall time complexity becomes n plus m plus m. Since m, the total number of bricks, is generally much larger than n, the time complexity simplifies to m. Now, looking at the space complexity, we start with the hash map edge underscore counts, which stores counts for unique edge positions. The maximum number of unique edge positions is determined by the total number of bricks minus the number of rows, or mn, as the last brick in each row is excluded. This means the hash map requires m space in the worst case. Beyond the hash map, other variables like edge underscore position, max underscore edges, and loop counters use only 1 space. Therefore, the space complexity is dominated by the hash map and is also m. To better understand the behavior of the algorithm, we can analyze it across the best, average, and worst cases. In the best case, all bricks align perfectly, resulting in only one unique edge position. The hash map edge underscore counts would then contain just one entry, and operations like insertion and finding the maximum are minimal. However, the time complexity remains m, since all bricks still need to be processed. For the average case, there are several unique edge positions, but fewer than the total number of bricks. In this scenario, the time and space complexity continue to be O, m. In the worst case, all bricks have varying lengths such that no two bricks align across rows. This creates n unique edge positions in the hash map, but even here, the time and space complexity remain O, m. To highlight the efficiency of the optimized solution, let's compare it to a brute force approach. A naive method would involve iterating through every possible vertical line across the wall's width and counting the number of bricks crossed at each position. This approach requires examining each brick for every vertical line, resulting in a time complexity of O, m*w, where w is the width of the wall. In contrast, the optimized solution focuses only on edge positions, leveraging the hash map edge_counts to efficiently count these edges and avoid redundant checks. This reduces the time complexity significantly to O, m. By prioritizing edge positions and avoiding unnecessary computations, the optimized solution achieves linear time and space complexity relative to the total number of bricks, making it far more efficient. When solving this problem, there are a few common mistakes that can trip candidates up. First, many people misinterpret the problem statement. Instead of minimizing the number of bricks crossed by the vertical line, some mistakenly try to maximize it. This misunderstanding can lead to incorrect solutions, so it's important to thoroughly read the problem and clarify any doubts with the interviewer. Another mistake is using a brute force approach inefficiently. For example, trying every possible vertical position across the entire width of the wall results in a time complexity of O, w*n, which becomes infeasible for larger inputs. Instead, you should focus only on the edges of the bricks where a vertical line could potentially pass through. Finally, edge cases are often overlooked. These can include walls with only one row, bricks of varying sizes, or cases where all bricks form a single column. Testing your solution against these edge cases is critical to ensure its robustness. Arithmetic errors can also be a source of mistakes. When summing brick widths to calculate edge positions, off-by-one errors or confusion with zero-based indexing can lead to inaccuracies. To avoid this, it's important to use clear variable names and validate your calculations using debugging tools or print statements. Another common pitfall is not handling large inputs efficiently. For example, walls with thousands of rows and wide bricks can overwhelm solutions with high time or space complexity. To address this, aim for optimized algorithms with linear time complexity where possible, ensuring your solution remains scalable even for the most demanding inputs. Now, let's discuss some helpful interview insights for this problem. One key optimization is to focus on the positions where brick edges align. Instead of iterating over every possible vertical line, you can use a frequency count of edge positions. The best position for the vertical line will correspond to the edge position with the highest frequency. This reduces the problem to a frequency counting task, which simplifies the solution significantly. It's also important to communicate your thought process clearly during the interview. Start by outlining a brute force approach, explain its inefficiencies, and then demonstrate how you can refine it into an optimized solution. Lastly, be prepared to discuss time complexity trade-offs. Compare the quadratic time complexity of a brute force approach to the linear complexity of an optimized solution, and explain why the latter is better suited for large inputs. This problem also shares similarities with other frequency-based problems, which can be helpful for building intuition. For example, LeetCode 560, subarray sum equals k, involves tracking cumulative sums using a similar frequency counting technique. In LeetCode 347, top k frequent elements, you identify the most frequent elements using a hash map, much like how we track the most common edge positions here. Similarly, LeetCode 451, sort characters by frequency, also emphasizes hash map usage for frequency-based sorting. Finally, LeetCode 1-2 sum is a classic problem that helps develop a strong foundation in using hash maps effectively to optimize solutions. Practicing these related problems can deepen your understanding of frequency-based approaches and hash map techniques. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves trying every vertical position and counting the number of bricks crossed. While this method is simple to implement, it's highly inefficient for large walls with a complexity of O, w*n. A more optimized approach involves using a hash map to count the frequency of cumulative edge positions. Here, the result is calculated as the total number of rows minus the maximum edge frequency, achieving a much more efficient O(n) time complexity. However, this method does require additional space for the hash map. Another less common approach involves using binary search for edge alignment, assuming that the bricks are sorted. While this can work, it's more complex to implement and rarely necessary in practice. Each method has its strengths and weaknesses, but the optimized edge frequency approach is generally the best balance of simplicity and efficiency for this problem. Great job! In this session, we explored LeetCode problem number 554, brick wall, and analyzed the optimal solution using hash maps. Remember to practice similar problems to strengthen these concepts. Thank you for your time, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!